The derivative can be interpreted as the instantaneous rate of change in applied context, or the slope of the tangent to the curve. So in this context, we have the volume of the balloon as a function of time, and if we differentiate the volume with respect to time, we obtain the instantaneous rate of change of the volume of the balloon at a particular time. So if we plot a few tangents here, we can observe that the balloon is initially easy to inflate, but as you keep inflating it, it gets more and more difficult until eventually the balloon bursts somewhere. And that can be seen by observing the behavior of the derivative. And the units for the derivative take on the units given in the applied context. So in this case, we have the volume of the balloon over the time in seconds, which matches the units of the derivative. The volume of an inflated balloon varies according to the function below. And what is the rate at which the balloon is inflated at 3 seconds? So in this context, the rate of change of volume with respect to time is equal to minus negative k by the maximum volume by e to the minus kt. And that's equal to 0.5 per second multiplied by 300 millimeters cubed multiplied by e to the negative 0.5 per second multiplied by 3 seconds. And be mindful of the units. So if we calculate this out, we obtain 33.5 millimeters cubed per second, which is consistent with the units on the left. We can use the derivative to solve rectilinear motion problems. So if we consider a particle travelling along this path, we measure the position from some fixed origin. So we draw an arrow from the origin to the particle, and similarly from the origin to x2. So these are what we call position vectors, which have a length and a direction. So using the graph, the particle ends up at position x2. And we define a displacement as a change in position, so the final position in the interval we're looking at minus the initial position. And as we can see, x2 minus x0 gives an arrow that points to the left. So in this case, the displacement is west or to the left. So the displacement is also a vector, having a length and a direction. Now distance, on the other hand, is the total length that the particle has travelled. So from x0 to x1 to x2. So the distance is a scalar quantity. It has no direction, but only a magnitude. We can define the average velocity as the change in position or displacement on the change in time. And that can be seen between 2 points on the position time curve. Now if we take the limit as delta t approaches 0, we obtain the instantaneous velocity. So you can see that the instantaneous velocity is the slope of the tangent to the position time curve at a particular time. And the velocity is a vector, which also has a length and a direction. So when the particle travels from x0 to x1, we can see that the velocity is positive. And at x1, the particle changes direction. So the velocity becomes 0, and from x1 to x2, the slope of the tangent to the curve is negative. Now another quantity to define is speed, which is a magnitude of the instantaneous velocity. So speed is a scalar. So you can imagine reading the speed of the speedometer of your car. It has no direction, but just a number. We can define average and instantaneous acceleration. So the average acceleration is the change in velocity on the change in time. So here you can see that the velocity is linear. So between any 2 points on this curve, you can see that the slope is constant. And if you take the limit as delta t approaches 0, we obtain an instantaneous acceleration, which is the slope of the tangent to the velocity time curve at a particular time. And you can see that this is also constant. So from x0 to x1, we have a velocity, and the particle changes direction when the velocity is 0 and then travels west. So because the acceleration is always negative, then from x0 to x1 it points this way, and from x1 to x2 it also points to the left. So therefore the acceleration is a vector quantity. So when the acceleration points against the velocity, the particle is decelerating or slowing down, and when the acceleration points in the same direction as the velocity, the particle is accelerating or speeding up. We can connect the position, velocity and acceleration using the position time curve and observing the behavior of a few tangents to the curve. So over the first interval of motion from x0 to x1, we can observe that the tangents are always positive. So therefore, the velocity is greater than 0 at a particular time t. And if you compare two tangents, you can see the velocity is decreasing. So the acceleration is a change in velocity over time. So therefore the acceleration is negative. Now in the second interval of motion, we can see that the slope of the tangent to the curve is always negative. So therefore the velocity is less than 0. But the slope of the tangent is increasing in a negative direction. So therefore the acceleration is less than 0. So in this interval, the particle is decelerating. And in this interval, from x1 to x2, the particle is accelerating, because the velocity is in the same direction as the acceleration, which is negative or west or to the left. The motion of a car is described by the following equation, and we're given the following initial conditions, and we're asked what is the rate of change of position over time. So that would be the velocity, which is the first derivative of position with respect to time. So that would be v0 plus 2a0t. And the acceleration is the second derivative of position with respect to time, or the first derivative of velocity with respect to time. So that would be 2a0. And substituting for the initial conditions and a time of 5 seconds gives us the velocity is equal to 44 meters per second. And the acceleration at 5 seconds is equal to 2 by a0, which is 6 meters per second squared. And note the units for the derivatives are consistent with the result. The motion of a particle is graphed below. And at what time does the particle change direction? Well, the velocity is the slope of the tangent to the position time curve. And when the velocity is 0, so that's when the particle changes direction at 1 second. Now part B asks what is the total distance travelled. So the particle starts from 0 and goes to 1 meter, and then from 1 meter it travels to minus 3 meters. So effectively it's travelled a total distance of 5 meters. And part C asks us what is the average velocity from t equals 0 to 3 seconds. So the average velocity is a displacement on the change in time. So the displacement is the final position minus the initial position over the final time minus the initial time. So what we get is minus 1 meter per second, which is the same thing as 1 meter per second west or to the left, because the velocity has a direction. The velocity of a particle is graphed below, and at what time does the particle change direction? Well, as we can see, at 3.5 seconds and 8.5 seconds, the velocity is 0, so that's when the particle is changing direction. Now part B asks, is the particle accelerating or decelerating at 4 seconds? Well, at 4 seconds, the velocity vector points to the left because the velocity is negative, and the acceleration vector also points to the left because the slope of the tangent to the velocity time curve at 4 seconds is negative. So therefore the particle is accelerating because both vectors point in the same direction. And what is the average acceleration between 7 and 10 seconds? So the average acceleration is the change in velocity on the change in time. And I'll leave this for you to work out and post your answer in the comments. The motion of a particle is described by the following equation. And let's determine the velocity and speed at a time of 3 seconds. So because we're asked to determine these quantities, at a particular time, they're instantaneous quantities. So the velocity is the first derivative of position with respect to time, and the unit is in meters per second. So always check that against your derivative. And substituting 3 seconds, we obtain minus 42 meters per second for the instantaneous velocity at 3 seconds. And because we got a negative result, the velocity points to the left or west. So the velocity is a vector which has a magnitude and a direction. Now speed, on the other hand, is the magnitude of the instantaneous velocity. So that's equal to 42 meters per second. And speed is a scalar quantity, so it has a magnitude but no direction. Given the following equation, which describes the position of a particle as a function of time, we're asked to determine the displacement and total distance travelled between 3 and 5 seconds. We'll recall that the displacement is equal to the final position in the interval of motion we're looking at minus the initial position. So therefore the displacement is minus 172 meters. And because it's negative, it points to the left or west. Now to find a total distance travelled in that interval, we need to see if the particle changed direction. And to do that, we obtain a velocity, and setting this to 0, so we take the positive root because time is positive, so the particle changes direction outside this interval. And consequently, the distance has the same magnitude as the displacement, because the particle did not change direction between 3 and 5 seconds, so the total length travelled is 172 meters. And distance is a scalar, so it's only a number without a direction. Given the following equation that describes the position of a particle as a function of time, we're asked to determine the instantaneous acceleration at 3 seconds and the average acceleration between 3 and 5 seconds. So differentiating the position with respect to time gives the velocity, and always check your units, which should match the derivative, and then differentiating again gives the acceleration. Now the instantaneous acceleration at 3 seconds is minus 36 meters per second squared. And acceleration is a vector, so a negative result means it points to the left or west. And the average acceleration is the change in velocity on the change in time. So if you substitute 5 and 3 seconds in this equation, we obtain the following result. And because the average acceleration is negative, it's a vector that also points to the left or west. The motion of a particle is described by the following graph, and we're first asked to identify the times where the particle changes direction. So that occurs at times where the slope of the tangent of the curve is 0, which is around 3.5 and 8.5 seconds. Let's estimate the displacement and distance travelled between 1 and 10 seconds. So the displacement is the final position in the interval we're looking at minus the initial position. So at 1 second, the initial position is 25 meters, and at 10 seconds the final position is around 34 meters. So therefore the displacement is positive, meaning that it's a vector that points east or to the right. And a distance can be obtained by visualizing the total length that the particle travels from 1 to 10 seconds. So have a go at finding the distance and post your answer in the comments. The motion of a particle is described by the following position time graph, and what's the average velocity between 4 and 6 seconds. So the average velocity is the change in position or displacement on a change in time. So at 6 seconds, the particle's at 36 meters, and at 4 seconds it's at 45 meters. So the average velocity vector points left or west. Now is the particle accelerating or decelerating at 4 seconds? Well, at 4 seconds, the slope of the tangent to the curve is negative, so the velocity is less than 0, or the velocity vector points to the left. And if we also take a tangent close to this point, well, you can see that the velocity is increasing in a negative direction, because the slope of the tangent to the curve keeps getting steeper. So therefore, the acceleration of the particle, being the rate of change of the velocity with respect to time, is also less than 0. So because the velocity and acceleration vectors point in the same direction, the particle is accelerating. The concentration of a reactant in a chemical reaction varies as follows, where A0 is the initial concentration in units of molar and K is the rate constant in units of 1 second. And part A asks us to write an expression for the rate at which the reactant decays, which is the rate of change of concentration with respect to time. So that will be minus K by the initial concentration by e to the minus kt, which is in units of molar per second, given that A0 is in molar and K is in 1 second. And part B asks us to determine an expression for the half-life, which is the time at which the concentration becomes 1/2 of A0. So we substitute A0 on 2 is equal to A0 by e to the minus kt, and cancelling A0 and taking the natural log of both sides, we get the natural log of 1/2, or the natural log of 2 to the minus 1, equals minus kt, and we write 1/2 to signify the half-life, and using the log rules and dividing through by minus k, we get the half-life is equal to the natural log of 2 on k. A cash deposit of $4,000 grows according to the following equation, where the interest rate is 2% per annum or per year. And how fast does the deposit grow at 2 years? So in this context, we're taking the rate of change of the deposit with respect to time, because we want to find the instantaneous rate of change at a particular time. So that gives the following result, and check your units. So the interest is in units of per annum or per year, multiplied by the time in years, makes this term dimensionless. And here we have the deposit in dollars by the interest rate, which is in per year, and that's consistent with the units of the derivative. So simplifying this and substituting a time of 2 years gives the following result. So at 2 years, the deposit grows at a rate of $83 per year. We will encounter related rates problems as worded problems, and here is a simple example where the area of a square is decreasing with respect to its length at a rate of 0.2 meters squared per second. So that gives us a clue that we should use the area, which is related to the length x, and the problem is basically giving us a rate of change in meters squared per second, meaning that we need to differentiate the area with respect to time. So we're assuming that x is a function of time, and using the chain rule, which is the basis of related rates problems, and you can see that we're told to determine the rate at which the length is decreasing when the length is 2 centimeters. So because the area is decreasing, we need to put a negative sign behind this derivative. So it's decreasing at this rate at a specific length of 2 centimeters, and observing our units when we divide through by 2x, and we obtain the following result. And that matches the units of the derivative on the left. The volume of a cylinder is increasing with respect to its height at a rate of 0.1 meters cubed per second. So the volume of a cylinder is pi by the radius squared multiplied by the height. And we're asked to determine the rate at which the height is increasing if the radius is 3 centimeters. So therefore the rate of change of volume with respect to time is equal to pi by the radius squared, which is constant, multiplied by the rate of change of the height of the cylinder with respect to time. And now we can substitute our values. So 0.1 meters cubed per second is equal to pi by the radius squared. So that will be 0.03 meters squared multiplied by the change in height with respect to time. And then solving for the rate of change of height with respect to time, we get 35.4 meters per second. And check your units. A 2 meter ladder is sliding down the wall at 5 meters per second, and we're asked to determine the rate at which the ladder slides along the floor when the bottom of the ladder is 1.5 meters from the wall. So using Pythagoras' theorem, the horizontal distance squared plus the vertical distance squared is equal to the length of the ladder squared. And then differentiating both sides of this equation using the chain rule, we get 2x dx dt plus 2y dy dt is equal to 0 because the length of the ladder is constant. And now we can cancel out the 2's and substitute some values in. So x is 1.5 meters by dx dt, and then plus y, which we can obtain using this equation. So that will be 1.3 meters multiplied by dy dt. So the ladder is sliding down the wall, so we have minus 5 meters per second, and that's all equal to 0. And now we can solve this equation and obtain dx dt. So that would give us 4.4 meters per second. And check your units. An ice cream cone has a radius of 5 centimeters and height of 15 centimeters. And ice cream melts and drips out of the cone vertex at a rate of 0.01 meters cubed per second. So we know the volume of a cone is 1/3 pi r squared h, and we know the ratio of the height to the radius of a cone is constant. So in this case it's 15 centimeters on 5 centimeters, which is 3. So what we have is h is equal to 3r, and we can substitute for the volume. So we get v is equal to 1/3 by 3r by pi r squared, which is pi r cubed. And we can take the derivative of the volume with respect to time, which gives us 3 pi r squared dr dt. And you can substitute for the radius and the rate of change of volume with respect to time, and that'll give you dr dt. And then we can differentiate this expression, so dh dt is equal to 3 dr dt, and then you can substitute for dr dt, and that's going to give you the rate of change of the height with respect to time. So post your numerical answer in the comments section. We can use the derivative, or the slope of the tangent to the curve at x, to approximate the value of the function at x plus delta x. So given that the derivative is the slope of the tangent to the curve at x, which is basically the slope of this tangent line, so you can see that multiplying the derivative by delta x is going to give us this distance, and adding the result to our known value of f of x, we obtain the approximation to the value of the function at x plus delta x. And this is useful, for example, where we have the square root of 4.001 and don't have a calculator, and we'll see the usefulness in example problems. So as we can see, the exact value of the function, and therefore we're going to get some error in our approximation depending on how large delta x is. So typically we use a small delta x to get a good approximation to the function. Given the radius of the circle is r, And suppose I measure the radius with some error, delta r. And what I want to know is the error in the area. So the exact value of r gives us the exact area, and the measured value of r gives us the area with some error. So here we have delta a on delta r, which gives us the slope of this secant line. And if we multiply by delta r, this gives us delta a. Now because the error in our measured values is quite small, we typically write this in differential form. And the derivative can also be written as a dash of r. And this here is a general expression which we can apply to different problems. So for example, we can also have the error in the volume of a sphere. And we'll apply this to some practice problems. Let's use the derivative to approximate root 4.01. And remember, the linear approximation to a function is approximately equal to f of x plus df dx multiplied by delta x. And in this case, f of x is equal to root x, or x to the half. So therefore the derivative of x with respect to x is 1/2 x to the minus a half, or 1 over 2 root x. And if we choose x is equal to 4.00 and delta x is equal to 0.01 in accordance with this square root, then our approximation becomes the square root of 4.00 plus 1 over 2 root x, which is 2 root 4, and that's multiplied by 0.01, or 1 in 100. So that gives us an approximation of 2.0025, and if you evaluate this in your calculator, you'll get a very close result. Let's approximate 1.98 cubed using the derivative. So the linear approximation to a function is approximately f of x plus the first derivative of f with respect to x by delta x. And in this case, we have f of x is equal to x cubed, so therefore the derivative is 3x squared. And if we choose x is equal to 2.00 and delta x is equal to minus 0.02 in accordance with this value, then what we get is our approximation is equal to 2 cubed plus our first derivative, which is 3 by 2 squared, and that's multiplied by delta x. So that gives 7.76. And if you evaluate this in your calculator, you'll get a similar result. Let's approximate cosine 47 degrees using the derivative. So remember that the linear approximation to a function is equal to the function plus df dx by delta x. And in this case we have f of x is cosine x, so therefore the derivative of f with respect to x is equal to minus sine x. So in this case we need to use radians. So if we choose x is equal to pi on 4, or 45 degrees, then delta x is equal to 2 degrees by pi on 180 to convert it into radians. And therefore our approximation becomes cosine pi on 4, and then plus df dx, which is minus sine pi on 4, and that's multiplied by delta x, which is pi on 90. And if you calculate this out, we'll get 0.682. And if you evaluate this using your calculator, you'll get a very close result. The measured radius of a sphere is 50 centimeters with an error of 0.1 centimeters. And what is the error in the volume of the sphere? So the volume of a sphere is 4/3 pi r cubed, and therefore the differential change in the volume is effectively 4 pi r squared dr. So just differentiate with respect to r. And now we can find the error by plugging in for r, which is 50 centimeters, and multiply that by dr, which is 0.1 centimeters. And multiplying this out, we get 3,141.6 centimeters cubed. And I'll leave it for you to calculate the actual volume of this sphere using this radius, and you'll see that this error is very small compared to the actual volume of the sphere. Let's derive L'Hopital's rule for an indeterminate limit of the form 0 on 0. So if we start off with a definition of these derivatives, and now if we divide these two together, and here we've assumed that the functions f and g are both differentiable, and the derivative of g at c is not 0. Now for the special case, where both f of c and g of c are both 0, and now as x approaches c, we have a ratio of 0 on 0. And we can also write this ratio of the derivatives at c in the following limit form. And by L'Hopital's rule, taking the limit of the functions is the same as taking the limit of the derivatives, where we have the indeterminate form 0 on 0. So let's quickly have a look at this example. So as x approaches c, we can see that we have an indeterminate form of 0 on 0. So if we take the limit of the ratio of the derivatives, so we can observe that the derivatives become the same as x approaches pi on 2. And this is true from both sides. Let's derive L'Hopital's rule for the indeterminate limit of the form infinity on infinity. So we're going to start with the definition of both derivatives and then divide them together. And we've assumed that f and g are both differentiable at c, and g dash of c is not 0. Now if we look at a special case where f of c and g of c are both large numbers that approach infinity, then what we get is a limit of infinity on infinity. Now rewriting this limit as follows, and you can see that we did not alter it, and now you can observe that we have a limit of 0 on 0. And we've already shown that L'Hopital's rule is valid for indeterminate limits of the form 0 on 0. So we use the quotient rule in the numerator and denominator. And now doing a bit of algebra, and now using the product rule for limits and cancelling out the negatives, we can evaluate the first limit. And for the second limit, we can also apply the product rule and recognize that this limit is f dash of c on g dash of c. And we've thereby shown that L'Hopital's rule works for limits of the indeterminate form infinity on infinity. We've evaluated this pretty standard limit previously using the squeeze theorem, and now let's evaluate it using L'Hopital's rule. So we can see that this is an indeterminate limit of the form 0 on 0, so we can take the derivative of the functions in the numerator and denominator. And therefore, we obtain cosine 0, which is the same result we got using the squeeze theorem. We've also evaluated this standard limit previously by using some algebra and using this standard limit. But now let's evaluate the limit using L'Hopital's rule. So if we substitute 0 for x, we get an indeterminate form of 0 on 0. So therefore we can take the limit of the ratio of the derivatives. So in the numerator we get minus sine x, and in the denominator we get 1. So therefore the limit evaluates to 0, which is the same as our previous result. We've also evaluated this limit by multiplying the numerator and denominator by the reciprocal of the fastest growing term. But here we'll use L'Hopital's rule. So we can see that x goes to infinity in the numerator and denominator. So this is a limit of the indeterminate form infinity on infinity. So we can apply L'Hopital's rule. So differentiating the numerator and differentiating the lower function. So we still have an indeterminate limit of infinity on infinity. So we apply L'Hopital's rule again, and it's still indeterminate. So we differentiate again. And this gives 18 on 5, which is the same as the quotient of the coefficients of the fastest growing terms in the numerator and denominator. Let's evaluate the following limit of the product of two functions as x goes to infinity. So we can write this limit as a limit of x squared on e to the 3x as x goes to infinity. And as we can see, this is a limit of infinity on infinity, because both of these functions go to infinity as x goes to infinity. So we can thereby take the limit of the derivatives of those functions. So the limit as x approaches infinity of 2x on 3e to the 3x. And this is still a limit of infinity on infinity. So therefore we can differentiate again. So we have the limit as x goes to infinity of 2 on 9e to the 3x. And therefore this becomes 2 on infinity, or 0. Let's evaluate the following limit as x goes to 0. So if we substitute for x equals 0, we get a limit of 0 on 0, and we can apply L'Hopital's rule. So differentiating the function in the numerator, we get the following result, and in the denominator we get 1 minus cosine x. And this is still a limit of 0 on 0, so we can apply L'Hopital's rule again. So if we differentiate sec squared x, you're going to get 2 sec x by sec x tan x. And then we differentiate the function in the denominator, and that gives sine x. So we can use trig identities to simplify the expression. So we get 2 by sec squared x, which is 1 over cosine squared x. And tan x is sine x on cos x. And divided by sine x, which is 1 over sine x. And sine x cancels, and 2 on cosine x cubed, where x equals 0, gives us a limit of 2. Let's evaluate the limit as x approaches 0 from the right hand side. So if you substitute for x, you're going to get a limit of infinity on infinity. So we can apply our L'Hopital's rule. So the natural log of tan x is basically 1 on u by du dx, which is sec squared x. And in the denominator, we get the natural log of sine x. So we have 1 on u multiplied by du dx. And now we can use some trigonometric simplifications. So what we have is cosine x on sine x by 1 over cosine squared x. And that's divided by cosine x on sine x. And therefore these two are going to cancel, and we obtain 1 over 1, which is 1. Let's evaluate the following limit. So we have cosec x in a denominator, which is 1 on sine x, and 1 on sine pi gives us a limit of infinity, and in the numerator, cosine pi is -1, so we get a limit of 0. And while L'Hopital's rule will work for this indeterminate form, we haven't proven it, and even if we applied L'Hopital's rule, the derivatives would give us a more complex expression to evaluate. So if this is 1 on sine x, then what we get is sine x by cosine x plus 1. And then if you break this up into the product of two limits, we'd obtain 0 by minus 1 plus 1, which is 0. Let's evaluate this limit. So if we substitute x equals 1, we get a limit of 0 on 0, and we can apply L'Hopital's rule. So we can actually simplify this limit by using the product rule for limits, and then multiplying and cancelling the factors out. But let's continue with L'Hopital's rule. So using the chain rule in the numerator, and the product rule in the denominator, and we can see this is still a limit of 0 on 0, so we'll apply L'Hopital's rule again. And now if we substitute x equals 1, we no longer have a limit of 0 on 0. So we obtain 0 on 6, which is 0. Let's evaluate the following limit. So if we substitute x equals 0, we get the natural log of 0 on a natural log of 0. And note that the limits of the upper and lower functions both approach negative infinity, so the negatives will cancel out anyway. Now recalling our trig identities, using right triangles, we can write the upper function as the natural log of sine x. And this is still a limit of infinity on infinity. So now applying L'Hopital's rule, we can use a chain rule in the numerator, and the derivative in the denominator is 1 on x. So we can rewrite this as follows, and the reciprocal of the cotangent is tan x. So 1 on tan x is equal to cotangent of x. And now you can see we have a limit of 0 on 0, so we can apply L'Hopital's rule, and the reciprocal of sec squared x is cosine squared x, so what we get is cosine 0 squared, which is equal to 1.